All right, here we're talking about what is a radian and how to convert between radians, degrees, and vice versa. So a radian, the angle measure when the arc length is equal to the radius. I have some kind of circle and an arc length that happens to equal the radius of that same circle. Whatever size gap that would create from the center of the circle so that this arced curved path was equal to the linear radius path, we were equal, that would create a 1 radian sized gap. How many radians would it take to get a full revolution? Right, our circumference formula tells us how many radian lengths it takes to get all the way around the edge of a circle, and that corresponds directly to how many radians it would take stacked up next to each other to complete this full wheel here. So 2 pi radians would equal 160 degrees, something we're a little bit more familiar with. Now they cut this down a little bit. They're both divisible by 2. We usually see 1 radian equal to 180 degrees. And if we cut that down any further, we'd start getting fractions of pi, so it doesn't really go further than that. Degrees to radians, let's say I got 130 degrees in play. I need to multiply something that won't change the size of that angle, it'll just change its units. So I want to maintain it, I got to multiply by some form of 1, and I want to do it in such a way that offsets my degree units, so they'll cancel, and introduce my radian units, because that's the answer unit I want it in. So I need some amount that has the same value in the numerator and denominator, and so we reach up here and grab this pi over 180. 180's got to be in the bottom, so it cancels units. I get in the numerator 130 pi radians, and the only thing in the denominator right at this point is 180. And so we cut that on down, 13/18 pi, that's exactly how many radians 130 degrees were. Going the other way, radians to degrees, they often give it and leave it in terms of pi because it's irrational. Let's say we got something like 4/9 pi, and I want to convert that to degrees. So again, I'm just multiplying by a form of 1, value doesn't change, just the units. I'm going to put my radians in the bottom this time because I don't want them any longer, and my degrees in the top because that's what I want as my final answer unit. So again, I'm using the same conversion rate, it's just essentially flipped, 180 over pi because they have equal value, and then I kind of cancel out. This pi is really up there with that 4 in the numerator. Those pi's cancel. 9 and 180 are offset. I see a multiple there quickly as 2 or 20. And so the only thing left here in the numerator, my radian units canceled. I have 80, and my only unit left is degrees. 4/9 pi equals 80 degrees. Here we have degree subunits. Sometimes a degree is just simply too big of a gap, especially if the circle is the size of the Earth. So you can split 1 degree into 60 minutes, 60 tiny little slivers, indicated by this 1 hash mark here, or each minute can also be split into 60 seconds, even tinier slivers, indicated by this double tick mark here. So you might be asked to convert something in all 3 units back into a decimal form for degrees, and you just got to remember to divide everything by 60. It's all a base 60 system. So 10 divided by 6 will tell how many minutes that was worth, 0.1667 minutes. And then I'm going to take all those minutes into a degree. I divide that whole unit by 60, another base 60, and I get 27.7028 degrees. So that's all these subunits converted just into degrees, and it's just going to be a small amount of them compared to a degree. If I need to add 2 things spread out in this many subunits, I just again start at the smallest unit, just remembering it's all base 60. So 40 plus 20 is 60. So all those 60 seconds gets to upgrade to 1 new minute. And I'm adding all these, I get 81 minutes. And then realizing that 60 of those will get to upgrade. So 60 of those get to make 1 degree, and that cuts it down to 21 minutes. And finally, I'm just adding up just normally here. I get 16 and 3, 4, 5, 56 degrees and 21 minutes is my final answer. We're talking about revolutions per minute, or RPMs. They could be asking about the angular speed or linear speed. So an example of that would be a Ferris wheel with a diameter of 10 meters is spinning at 5 revolutions per minute. So the angular speed is just simply saying how many degrees have you gone through every minute, how many radians have you gone through every minute. So I take a full revolution of degrees, 360, times how many times it's going to happen, 5, and I get a 1800 degree per minute speed. If I had to do it in radians, or has to do it in both, I would say instead of 360, 2 pi. That's a full revolution. That's happening 5 times, 5 RPMs. So that's just going to be 10 pi radians per minute. The linear speed, if you're actually sitting in a cart on this thing and the distance you traveled as you went around the Ferris wheel 5 times, we're going to have to rely on our circumference formula, 2 pi r. And how many times did you travel that circumference? References the RPM again, in this case, 5. I'm going to substitute in my radius, which also happened to be 5. My diameter is 10. My radius is 5. I lump up all those coefficients together. 5 times 2 times 5 is going to give me a 50 pi. And make sure I get my units right. My radius was in meters per minute, because that was my revolutions per minute. And so those are my 2 answers for linear speed, or my degree angular speed, or radian angular speed. All right, here we have arc length and sector area. We're going to be doing them both in degrees and radians. So an arc length is recognized as a piece of the circumference. So that circumference formula is going to be a big part of this arc length formula. So 2 pi r gets you the whole circumference, and to figure out how much portion you actually have is going to rely on the theta, the actual central angle. So you're going to throw that over a complete circle of 360, and that's going to give you the portion of the circumference you also happen to have. Down here in radians, the only thing that changes here is that 360 becomes a 2 pi. If your theta is in radians, you need to put over a radian comparator here. So 2 pi times circumference. And because this 2 pi is in the denominator and this 2 pi is in the numerator, this can be simplified to the equation theta times radius. So in radians, the arc length could just be the size of the angle times the size of the circle, radius, and you'll get your answer there. If I'm talking about the sector area, that's talking about a piece of the area of that circle. So the area formula is going to be involved. Instead of 2 pi r squared. Get you the area of the entire circle, theta over 360. Get you the size piece of pizza you have, right? The size of the pie you have. So that's going to be a portion of the area. Done. If I jump down here into radians, that 360 is just a 2 pi. If theta's in radians, over 2 pi. If theta's in degrees, over 360. Pi r squared, still present. That's still a formula, regardless of whatever unit it's in. I get a little bit of cancellation with those pi's, so this could be simplified as theta radius squared over 2. We're going to be talking about sine, cosine, and tangent in relation to a unit circle. Unit circle just means a circle with a radius of 1. And so the sine, cosine, tangent ratios individually. Sine is the opposite over hypotenuse. Cosine adjacent to hypotenuse. Tangent opposite over adjacent. Now the way that corresponds is we kind of superimpose that on a unit circle. If we go along this rim and drop down, we could generate right triangles of every size and every quadrant of every possible conceivable combination there. And the brilliancy of here putting on a unit circle is all the hypotenuses will be 1. And that is the denominator of both the sine and cosine function. So I have denominators of 1 in both those cases. So when I boil it down, the sine ratio would just correspond to the y-coordinate for sine. For cosine, it would just correspond to the x-coordinate. That being the adjacent and the hypotenuse just always being 1. And then tangent could be the y-coordinate over the x-coordinate. But there's certainly better ways to think about tangent. If I were to graph these, take each one of these cases and kind of plot it on a coordinate plane, you can start seeing where that sine, cosine wave are generated from. At angle 0, sine has a ratio, its opposite side has no length over hypotenuse. So 0 goes to 0. The highest ratio sine can achieve is 1, because that would be assuming that the opposite side could somehow be bigger than the hypotenuse, so that ratio is never going to exceed 1, because the opposite side cannot be more than hypotenuse in any case. -1, and it takes a full rotation all the way around this circle to get all the positive and negative variance of that sine wave. Cosine wave is similarly shaped, it's just starting at a different point. It's following the x-coordinate. So over here at angle 0, x has a value of 1, or the adjacent side has the same length as the hypotenuse. So for both those reasons, it starts at 1, its biggest ratio, and then from there it goes down to its lowest ratio and then back up. Negative 1 again for him, and that takes 360 to go all the way around that. Now tangent isn't as restricted, right? These are just a ratio of the two side lengths. So they can certainly be, one can be longer than the other or shorter than the other. So you're not restricted, you don't have this tight range as a sine and cosine. So at time 0, right, you're asking, what's the y coordinate over x coordinate, or what's the opposite side over the adjacent side? Either case, it's going to be 0. Ratio is 0 at 0. And then something unique happens. This kind of starts skyrocketing up into infinity and diving down to negative infinity, and actually has these asymptotes at places where your denominator starts bottoming out, right? It can't have a denominator of 0. So where does the x coordinate equal 0? 90 and 180. Or in this window I have here, that would be, 90 degrees. And back here would be negative 90 degrees. But of course, that would keep happening over and over and over. Continuing infinite amount of asymptotes as well for tangent.